So in this video, we want to look at the concept of change in momentum of a system or change in momentum of an object. In the previous video, we have just seen how we calculate the resultant momentum at a particular instant of time. For example, we have a system with more than one body or with more than one particle, and we want to find out, if we treat that as a single system, what is the total momentum. This one is different from that situation in the sense that it was at a particular instant of time that we found out what is the total momentum of the system. Over here, this system has got only one particle, but after a certain duration of time, maybe like, for example, 10 seconds, its momentum changes to a different value altogether. How do we know that? The velocity has changed. And since the velocity has changed, momentum has changed. So how do we calculate the change in momentum? So let's first of all start by calculating the first momentum here and call it initial momentum, which is of course 1500 times 20, and that will give us 30,000 Newton seconds, and this is to the right. Of course, this is a vector. We said it's optional. You can either put that arrow or fail to put it. There is no problem. Then after a time of 10 seconds, its final momentum becomes, again, 1500 times 25. We are going to get 37,500 Newton seconds. So how much is the change? Of course, you'll tell me it is 7,500 Newton seconds, which is correct. That is a change in momentum. Change in momentum is a vector. I'll ask you, what is the direction of that change in momentum? Of course, in a simple situation like this, you should always know that the change in momentum of this system is in the direction of the final momentum. The final momentum. Just observe those 2 points, because when it comes to calculating the change in momentum, we will do final momentum minus initial momentum, and this will be 37,500 minus 30,000 Newton seconds, and you get 7,500 Newton seconds to the right. And you can see it is in the direction of the final momentum. This is the final momentum, and it is to the right. That situation is easy. But suppose the particles were not moving in the same direction. What will be the direction of the change in momentum? Let us use the same situation, but this time I want to use the idea of head to tail. So I want you to realize that this can be written as this. After all, subtraction is a special case of addition. When you subtract one physical quantity from another, it's like you are adding that physical quantity, but you have changed its direction. The negative sign indicates that you have changed the direction. So this is what we are going to have. The final momentum, which is this one, if I use the same scale of 1 centimeter representing 1000 Newton seconds, this will be 37.5 centimeters, and it will be a longer arrow like that. And then plus. This negative sign will show that the direction of the initial momentum, which is to the right, now has been made to move to the left. That is the meaning. So that you can see the negative sign has disappeared from here, and you can see it's as if I'm just adding 2 momenta. using the head-to-tail method. And that's a concept that I'd like you to get, because if you get that, it will solve all problems or all questions that relate to this kind of situation, especially when we have an object, for example, a tennis ball hitting a wall and then bouncing from the wall. That one is a common question in most situations at our level. How do we handle the change in momentum? We deal with it like this, and I'll show you how easy it can be, because if this one is 37.5 centimeters and this is 30 centimeters, then you will definitely be able to see that once I have that 7.5, and then I have this, I connect the two head to tail, then if this is 37.5 centimeters and this is 30 centimeters, then definitely this represents the resultant. This represents the resultant. Remember, I am adding these two momenta. I am adding them. Although the definition is change in momentum. Change in momentum, which is a subtraction, but I have cleverly converted it into addition of two vectors so that I can use a very simple method of head to tail. So remember, when you're confronted with a subtraction of two vectors, just treat it like addition and you are done. For example, now this one will give me 7.5 centimeters. And the reason why I'm doing this is to get the direction of the change in momentum. And you can see it is obviously to the right, and there is no doubt about that. I just need to go to my scale where I said let 1 centimeter represents 1,000 Newton seconds, and I'll be able to see this on 7,500 Newton seconds to the right. Remember, I asked you, what is the direction of the change in momentum here? And for this case, you can be able to see directly it is to the right. But supposing the directions were different, direction of this and this, they were not exactly in the same direction, what will you do? Now, the other situation is this. You may find that the velocity may reduce, may be smaller. You see, if it is smaller, you follow the same method. For example, if this car now is moving with 15 meters per second, you will find that now that change in momentum will be in this direction, to the left. What do I mean? If this velocity now changes to, let me assume that it is 15 meters per second. You find that the change in momentum, the second change in momentum, will be the final momentum, which will be 15 times this one here. And I think 15 times 15 gives me 22,500 Newton seconds. So I'm going to have the final momentum, which will be represented by this shorter arrow here pointing to the right, plus minus the initial momentum, which will be now be like that, which is 30 centimeters. Of course, this one will be 22.5. I hope you understand why I've done that. Okay, now let's see, when we connect them head to tail, we are going to have this one, and then we are going to have this one, and then this is where I started from, because this is where my first tail is. That's where my first tail is. And then my last head is here, and you can see now I move in this direction through a distance equal to 7.5 centimeters. So you can see the final momentum will be to the left of this match. Again, the final momentum is Again, the change in momentum has now a negative value. The change in momentum now has a negative value because we are taking the change in momentum to the right to be positive. Anything to the left will be negative. In the next example, we are going to look at a situation like this, but it is a situation where we have an object, like for example, a tennis ball. It is moving towards the wall. It moves to the wall, hits the wall, and then bounces from the wall. We want to tell, or we want to be able to calculate the change in momentum. But before we do that, let's go back here and realize that this is the change in momentum of this car, and that change has occurred in 10 seconds, and we can be able to calculate the rate at which that momentum changes. In which case now, we will be calculating the force. You see, if we divide these 7,500 Newton seconds by 10 seconds, the seconds are going to cancel, and we're going to get some kind of force which is 750 Newtons. The physical quantity we'll get has got the unit Newton, so it is a force. What force is that? It is the resultant force acting on this car. The forces acting on this car, there are basically two of them. There is the driving force due to the engine, and there is the air resistance. The resultant of those two forces, which must be to the right, is what now we are calculating here. But that will come later on. First of all, we have to deal with a situation where we want to know how do we calculate change in momentum and determine its direction. Let's look at the next example and see how we deal with it.